Good. Okay, so hi everyone, I'm Shuang. I'm a PhD student from the Knowledge Media Institute, the Open University, UK. So today I'm going to present my paper, Learning the ULMFiT and Self-Distillation with Calibration for Medical Dialogue System. So first, I will briefly talk about the calibration and why I choose to do this calibration. So basically nowadays, many of the state-of-the-art model have shown very high accuracy, such as for the sentiment analysis task or for the image classification, the accuracy can be 90 plus. And we are happy to see this. And it also means that the model is very confident to give us this kind of prediction. I mean, this is for the correct answer we expect. Then how about the wrong answer? How about when model give us the wrong prediction? Do we still expect the model to be very, very confident to give the wrong answer? Of course, it's not. So for example, when the accuracy is about 80%, we expect the model to produce the result with a confidence score like 80% also. So when accuracy is like 20%, we also expect the model to show us the confidence score about like 20%. But the reality is not. For many of the deep neural networks, the confidence score is too much high. So means when the accuracy is only like 20%, the confidence score can be still like 80 or 90%. This is not what we expect actually, especially for the because this will harm harm the model uncertainty, and especially in the very sensitive field or sensitive cases like the medical field. This is very important. So here we provide to calibrate the model. And for example, we can see from here, we have the model A and model B. They have the similar accuracy of 85%. But for the model A, the confidence score of we can say the probability is about is also about the 86%. But for model B, the confidence score is like 96%. So in this way, it's very clear that model A is very well calibrated, and then model B is miscalibrated. So we prefer the model like model A in this case. And basically for calibration, there are two techniques. One is the temperature scaling, another is the label smoothing. So in the paper on calibration of modern neural networks, it introduced how to integrate the temperature scaling to help to calibrate the model. So this chart, this is accuracy, and then this part is the confidence. So you can see that ideal case is that the accuracy and confidence are the linear relationship, and so means when the confidence is 0.2, the accuracy is also expected to be 0.2. And this gap marked as pink is the gap between the accuracy and confidence. So the bigger the gap is, the less calibrated the model will be. And then here is the temperature scaling equation. We apply this, this is denoted as T. So we apply this temperature scaling to the logic before pass to the softmax in this way. And then another method is the label smoothing. So in the NeurIPS paper 2019 by Hinton, when does the label smoothing help? It introduced the positive effect of the label smoothing for the calibration. So label smoothing means that for example in the image classification, we got 3 classes, and then generally the label is 1 hot, means it's 001 in this method. But for the label smoothing, because of the parameter alpha, we smooth the label into for example 0.7, 0.1, 0.2 in this way. So you can see from this diagram the training with the label smoothing and without the label smoothing. So the training with the label smoothing, you can see the classes the classes are better separated with each other. And then the transfer learning techniques are also commonly used in these tasks. And so here we are going to we use two transfer learning techniques. One is the ULMFiT, another is the self-distillation. So for the ULMFiT is the universal language model fine-tuning, and then basically the idea is like to model the large data set of the language, such as the Wikipedia, and so like the model to have a better feature extraction, and then for the following tasks. So basically, this is the idea for the ULMFiT. And then for the before introduce the self-distillation, I will introduce the knowledge distillation first. So the idea of the knowledge distillation that you train a big network or a big data set, and then you pass the information to a smaller data set. So in this way can increase the model performance. And then this is the KL divergence as the knowledge distillation loss. So you can see this T here is the temperature scaling, because temperature scaling is commonly applied in this in the KL divergence loss. So actually in the real world, sometimes we don't have that well-trained big data set or that good big model. So in this paper, they introduced another term is called self-distillation. So it means even with the smaller data set as the teacher data set or very poorly trained teacher data set, we can still get a very similar result. So in this way, we don't need the very big data set or the big model to train. So here is the research question. Does the calibration has relationship with the knowledge transfer techniques, such as the ULMFiT and knowledge distillation? We can divide this into three small questions. So does the calibration help the ULMFiT, help the knowledge distillation, and also help the whole model for the fine-tuning? So here is our proposed method. So first, we apply the label smoothing to the ULMFiT, and we apply the temperature scaling to the self-distillation, and then we apply the temperature scaling for the whole model for the fine-tuning. And then speaking of the temperature scaling, there are two concepts of this. It's called the fixed and the optimal T value. So for the fixed T value, then we tune the T with the value of 1.5, 2, 3, 4, and 5. So we can see that the T value equals to 2 gave us the best accuracy. And then to get the optimal T value, we need this ECE first. ECE is called the expected calibration error. If you still remember the previous diagram, is the pink gap between the accuracy and the confidence. So the smaller the ECE is, the more calibrated the model will be. So to get the optimal T, we need to tune the T value to get the best ECE, and at the same time, we need to keep the cross entropy loss and the accuracy unchanged. So means if we just want to get the best ECE, and then we change the T into a too much big value, it will also harm the accuracy. So we need to keep this condition here to get the best T value. And then here is the data set we use. Because our field is the medical dialogue data set, and we create our own data set specifically for the back pain. And so we collect about 1,000 pairs about the conversation, including the inquiry from the patients and the reply from the doctor. And then we cover the 5 major factors that related to the back pain, such as sleep, nutrition, mental health, and so on. And then all the answers means all the replies has been validated by the medical expert. And then for this back pain dataset, to our very best knowledge, is the first medical dataset related to back pain. So and to validate our proposed method, we also use a much larger dataset. It's called the MedDialog dataset. So this one including like 0.26 million conversations, and it covers about 100 types of the diseases. And then here's the result. So the table 1 is the result with the back pain dataset. So the method we use is the baseline including the vanilla transformer and the ULMFiT. And then for the method, it's including the label smoothing and temperature scaling. So for the label smoothing, we apply to the ULMFiT, and then the temperature scaling to the whole model in this way. So the evaluation metrics we use is blue score 1, perplexity, recall precision, F1 meter, and the ECE loss. For ECE loss, the smaller the loss and means the better calibrated the model will be. So from the result, you can see that is the ULMFiT gave us the best blue score, and also the recall precision F1 and mentor, and then as for the ECE, is the temperature scaling gave us the better result. And then to validate this proposed method, this is the result from the MedDialog dataset. And from here you can see that if we talk about the blue score 1, is still the ULMFiT gave us the best blue score, and but if regarding to the precision F1 meter and the ECE is given by the fine tune with the temperature scaling. So from the whole result, we can see that no matter is the label smoothing or the temperature scaling, they are all the calibration techniques, and then it has a positive effect on the model performance. So here is the visualization of the predicted result, and then this is the sample, this is the question, this is the ground truth, and then here is the predictions by different methods. So we can see that for all these 4 methods, the ULMFiT generate the longest sentence, and it also add the verb. Let's say instead of just up or be up, it add the stand in here, the verb, and then also give the short period as the as for the condition of the time, and then for the fine tune this one, it generates this like gently to give the to make this advice more accurately. And then here is the result for the self-distillation with the back pain dataset. And then the method we call so-called standalone is the vanilla transformer and the ULMFiT. And here is the self-distillation with the fixed TS, which is and then the self-distillation with the optimal TS in this way. So we can see that it's still the ULMFiT gave us the best accuracy, even though we apply the SD with the TS in this way. And then also for the perplexity, recall precision, F1 and meter is all the ULMFiT outperform all other methods. And then as for the ECE is the better ECE is given by the SD with the TS with the fixed and optimal both. So in conclusion, in this paper, we show that the calibration can benefit the knowledge transfer techniques such as the ULMFiT and knowledge distillation. And also the temperature scaling actually help the whole model fine tuning. It can give the model better performance. And then, but the fine tuning is actually a 2-stage training, so which can cause the additional computational burden by somehow. And we can see that the ULMFiT with the label smoothing actually hurt the SD. So by this, we mean that this accuracy actually drop by applying the estimate the TS. And the further experiments will be applied, let's say, for more tasks in the NLP, like sentiment analysis, and also the computer vision, such as the image classification, segmentation, this kind of tasks. So thank you. Do you have any questions?